All right, I think we can start. Sorry, guys.
Yes.
um, Welcome to this week Autonomy Talks. This week is a great pleasure to have Diego Romeres. A bit about Diego. Diego received his master degree and his PhD from University of Padua, where he focused on Bayesian system identification, robotics, and machine learning. During his PhD, actually, he also visited some other university, among these TU Darmstadt and ETH, where he was working on power systems. So he's a known face. Currently, he's a principal research scientist at the Mitsubishi Electric Research Laboratories in Cambridge, in Boston. So these days he's feeling colder temperatures than the ones we are feeling in Zurich. And his research focuses on robotic manipulation, artificial intelligence, machine learning, reinforcement learning, and scientific identification, and system identification. And today he's going to show us some theoretic things, but also some applications in real life. So without further ado, please go ahead. The stage is yours.
Thank you, Jared. Thanks a lot. Thanks for the introductions. And thank you all for attending these presentations. I am quite excited to present and discuss with you all some of my works in reinforcement learning for robotics. Before starting, let me just briefly introduce about Mitsubishi Electric Research Laboratories, the company where I work. So we are part of Mitsubishi Electric, the mother company that is based in Japan. You can see here, and where there are two main big R&D centers there, but we have R&D centers through all Europe and also in Asia, China. We are actually the research laboratory centers located in Cambridge, next to Boston in the United States. And very briefly, I just would like to let you know that we are an industrial lab with 60 plus researchers, all with PhDs, and we are being exposed to problems coming from industry because of the relationship with our mother company. But we have, I would say, the luxury of publishing all our research as well in journals and conferences. And these are the main areas that we're focusing on: artificial intelligence, control, physical modeling, optimization, and signal processing. And we collaborate a lot with universities, and we are always looking for new collaborations with academia. Okay, now we can start. I would frame my research focus in a tentative of deploying learning algorithms into the real world. And here we can see some of the works we have been working on. For example, on the left, you can see this assembly task where there is a set of gears and pegs to assemble. This fairly complicated manipulation task where we have this elastic object, the belt that has to be assembled around the pulleys. And we have some more benchmark systems like this full-top pendulum and this circular maze where we had to roll the ball to the centers of the maze itself. And we will see the solution of some of these systems in the remaining of the presentation. But really the focus is to identify some of the main ingredients that we need to develop in order to deal with a variety of tasks. And so the question is, what are these ingredients and how we can solve these tasks in general? With this in mind, in the remaining of the talk, I will talk about these following algorithms, topics. I actually have to say that I realized that after I wrote the abstract, I've been a bit too ambitious in everything I wanted to say. So I reduced it a little bit, but I will still introduce reinforcement learning, and I will focus on model-based reinforcement learning and to its applications to robotic, but focusing on robotic manipulation problems. And in the second part of the talk, instead, I will focus on a specific algorithm that we recently proposed. And in the final part of the talk, instead, I will show you how we apply this algorithm to real systems and what were the main problems that we had to face. Okay, I assume that many of you are familiar with reinforcement learning, so I will make a very light introduction. This is kind of the classical pictures about RL, where there is this big brain that is the RL agent, and it is, if you want, our algorithm, our computer that decide on actions, and this action is implemented in the environment, and the environment changes on states. But what our algorithm can see from these changes is just an observations of the state and some reward signals. And based on that, we have to compute the next action in order to accomplish the task that we are trying to solve. And here I just cite one of the most classical textbooks on RL, that is Sutton and Barton. Probably when thinking about RL algorithms, all of you have in mind a set of different algorithms that they are also often grouped in different ways. In this case, I would like to group them based on their data efficiency. So how many samples they need in order to find the optimal policy. So starting from the right, from the least efficient, there are their own policy gradient algorithms. Some examples are TRPO, PPO, and you also had a contribution on extension of TRPO. But what we saw is that these algorithms are very powerful in terms of asymptotic performances, but they are very data eager. So moving on the left-hand side of the line, we have actor critic methods and then offline, off-policy algorithms, so that they basically reuse the data that they have been using during that they have seen on the real system from the real systems, like DQN and soft actor critic. And finally, we have the model-based RL category. That is going to be the main focus of this talk. And just to cite a few examples of these famous algorithms that are since they are the ones that have the best data efficiency, are also the ones that are most applied into physical systems. Some of them are guided policy search, PILCO, and in general, that is often used is just some machine learning model plus planning. Okay, now that we identified this class of model-based RL algorithms, I will first try to give a very high view of the anatomy of these algorithms. So usually we start with a policy execution, so maybe a random policy, or if we know something better, we can do something better. We apply to the systems, and we can collect some observations. Once we have the observations, we need to learn a model that is a function that, given the current state or state representations and the current actions, predicts what's the next state. And the benefits of having such a component is, again, as we said before, data efficiency, but also usually in general, we can have some either guarantees or analysis on the systems, and we can have models that are or should be task agnostic, so independent of what's the specific goal. After we compute the model, we can learn the policy. That is a function given the state outputs, the input, the control input for the system. And we can think of this as an optimization problems in general, where we define a cost function, the constraint that we want to satisfy. We need to have a way to simulate the policy and the trajectory thanks to the model that we learned in the previous block. And all the task specifications goes into this block. And once we learn the policy, we deploy it into our systems. And if it's a real systems, we cross our fingers and hope that we are not breaking anything and we achieve our task. And we keep repeating this loop until we learn an actual policy. Now, that we understood the general idea, I will go through this loop one more time, but discussing what I believe are some of the main points and presenting some of the high-level takeaways of my recent research. For reason of time, I will try to just point to what are the main highlights and try to give you these messages. If something is not clear, though, just stop me and I will try to repeat it again. So the first thing is that we said that we have these observations, but we know that the system has a real state, and then there is a layer of sensors that will give us the observations. And I think it's fundamental to keep considering multimodal sensing and fusing all these sensor modalities. Here I'm listing a few of them. The most famous one are probably encoders, force torque sensor, and visions like cameras. But recently the community is focusing a lot also in other modalities like tactile and text and voice. And for example, we have been working in tactile sensor lately, and we have experimented with these vision-based tactile sensors that you can see here on the fingers of the gripper. This sensor comes from the Alberto Rodriguez lab, that is professor at MIT, that collaborated in this paper. And here on the left, we can see the images that actually these tactile sensors are producing on real time. And the task here was doing the insertion of the box into this hole. And we see that at each poke, the algorithm, we are seeing the learn policy in the end, is able to find the action to correct the movement until the insertion. So the takeaways here were really that vision-based tactile sensors have a very rich, give us a very rich set of informations. And so that in RL algorithms, we can use this information to do insertion tasks without knowing any geometry on the object that we are manipulating a priori, and we can generalize to novel objects. For example, this box was not seen before, and the algorithm has seen different shaped objects and holes. And in general, we have saw that empirically, this kind of sensor can give advantages with respect to standard force torque sensors. Okay, moving forward to the model learning block, I would say that I believe the importance of using probabilistic models and in combining physics equation of motions with data-driven models. We will see much more of this later on in the presentations, but here I just would like to highlight a work that we have done recently with Professor Tenenbaum's group, in which we were learning how to control this maze system. As you can see here, the purpose is to roll the ball towards the center of the ball, of the maze, sorry. But the idea is that we used a physics engine model of the maze that was built in Mujoko, and we augmented it with reinforcement, with data-driven models, Gaussian processes in this case, and we solved in the whole task in only a couple of minutes. So these are fairly complicated systems because the dynamics has many nonlinear components, and in only a couple of minutes, sorry, of interaction with the systems, we solved it. And as you see here, probably the video maybe is a bit broken, but it's in general hard if there was not the labels to understand which one was the human solution, what was the other agent solutions. And we think that indeed when humans approach a problem, they already have an initial idea of the physics that is behind it. And we try to simulate this one with the physics of the physics engine. And then when we are actually solving the task, we just adapt our prior knowledge. And so this is really the purpose of this kind of task that I think it's a great opportunity for everybody to start working on. And proceeding into the policy learning block, as we said, we can see it as optimization problems. And what we are interested in is to update the policy to solve our task. And usually we have to take care of the problem of local optima, problem estimating the gradients. And in general, we want to have some safety constraints and possibly the capability of generalizing to multiple tasks, or at least to a family of tasks. And fundamentally is also how to simulate the policy, the trajectory, using the models that we obtain in the previous block. Regarding this, we try to solve this fairly complex manipulation task where we had to assemble this loop around the two pulleys that you can see in the background. And we did so by proposing to model elastic object with 3D key point representations. So we reduced the state space of the object, and we modeled the elasticity and the different contact modes with complementarity constraints. We can see here how the different contact modes are happening and what I mean by that. And we are soon going to release actually a general purpose software package to learn model-based controls of robotic systems like this one through nonlinear optimization problems, transforming the control problem into nonlinear problem. And we are doing so because we think that solutions of this kind are very helpful for the learning algorithms, in the sense that the community is trying to leverage more and more nominal trajectories, either coming from demonstration or from trajectory planners, because even if we believe that learning algorithms have a lot of potential of application into the real world. We should not learn everything from scratch, but we should exploit what we already have and then augment it and improve it both at the model level and at the policy level with learning algorithms. Finally, in the policy execution block, I would like to stress and emphasize the importance of considering low-level controllers when we are doing our policy learning, especially, of course, when you are dealing with real systems. Because even if we usually cannot change maybe the dynamics of the motors or the controller and the motor, we should take care of their dynamics, and we should include the transitory that they generate. We also had some works over here in how to implement these low-level controllers with machine learning models, Gaussian processes with in a feedback linearization scheme, control scheme. But for the sake of time, I will not talk about it in details. And the final things that I would like to see in this scheme of model-based RL is that on top of this, of the loop that we have seen so far, I think it is really important to start considering high-level planners. So the community is moving with many works in subtask discovery or skill learning, or even introducing the concept of curiosity and dreaming. So kind of imagining what are all the tasks that we could do with the system that we have in front of us without specifying specific task, or any way to identify all the subtasks in order to reach a bigger goal. And I think this hierarchical planning is going to be type of things is going to be fundamental for solving complex systems. And each of these subtasks could be solved, for example, by the scheme that we have seen, and I try to explain down here. With this, we have concluded the overview of some of the main ingredients that I think at least are important for model-based reinforcement learning algorithm, and in which I kind of try to share some of the main takeaways and my experience. And if there's any questions, I'm happy to take it. Otherwise, I would like now to deepen more into one specific algorithm that we recently proposed. And the name of this algorithm is Monte Carlo Probabilistic Inference for Learning Control, also called MC-PILCO. And this was in collaboration with the University of Padua. Beside all the mathematical details that we are going to see right now, the main properties of this algorithm, I would say they are, well, data efficiency, it's model-based, and the capability of handling uncertainty. And we will focus also a lot in the differences that there is between working simulation and real systems. Let me first just give a high-level overview of the algorithm. MC-PILCO is a model-based policy gradient. So we perform policy gradient search algorithm, and we use Gaussian processes to describe the system dynamics. And we rely on particle-based methods to approximate the long-term state distribution. The gradient of the expected cumulative cost that we need to compute is performed by backpropagations, and we are using kind of a famous trick that is called the representation trick in order to obtain this backpropagation. For who is not familiar, now we are going to see all these components one after each other. So this is the scheme that you are already familiar with, and that represent one of the trial of model-based RL, because model-based RL is composed by several trials. And in the model learning block, we are going to use Gaussian process regressions, and we will list what are our specific contribution into that. And in the policy learning, what we are proposing is to use Monte Carlo method, in which we simulate the evolution of m particles, in this case 2, for each of which is then we evolve each of the particles using the model that we learned in the previous block. Thanks to this, we can compute an approximation of the long-term term cost functions, and we can now use it in order to compute the gradient of the cost functions with respect to the parameters of the policy, and then do the policy update. For who is familiar with this kind of algorithms, we know that this general structure and using Monte Carlo methods is in general not new, and but it had several problems in the past, and that's why it was very hard to implement it into real systems. So now we are going to see what are our specific contributions in each of the blocks. Let's start from the model learning component. And model learning in general is the problem of defining a model, mathematical equation, mathematical law, sorry, that f that parameterizes some parameter eta, that given the state and the current input predicts what's the next state. And we do this by collecting a bunch of output and input and making an assumption of the model that is that the output are a corrupted version of the model, and the corruption is an independent Gaussian noise, in this case, EOK. We really ask ourselves, how do we model the forward dynamics F? And in my opinions, when we do that, we should use both the equation of motions and data-driven methods, whatever methods one is familiar with or thinks is appropriate for the applications. And we use Gaussian process regressions that I will briefly describe here. And so remembering that this is our assumption of the models, in Gaussian processes, what we do is that we give to the forward dynamics F a pi distribution that is a Gaussian with zero mean and covariant matrix K of eta. K is called kernel in machine learning, and eta is the set of hyperparameters that define our covariance function. An example of a kernel function is the square exponential or RBF kernel that is presented here. And for example, in this case, the hyperparameters would be lambda and omega. And one nice thing is that we can compute these hyperparameters, the optimal hyperparameters, in a principal way that is maximizing the marginal likelihood. And the good thing of Gaussian processes is that once we fixed these optimal hyperparameters, we know the full posterior distributions in closed form. So given a new point, x star, a new state, I can predict the full distribution, which is Gaussians. And so I can compute in closed form of the mean and the covariance. So I have a principal way to estimate not only my predictions, but also the uncertainties around it. Let me now just stress a bit more the importances of the choice of the kernel function that we use a priori, because we talk about the square exponential kernel, which is very commonly used and has some nice properties because it correlates inputs that are close to each other in some space, and it has smoothness properties, and so that's why it has been widely used. But this kind of kernel doesn't encode any property of the system that you are trying to model. So it could be used for any model, but of course there are some drawbacks on it. So what we are trying to, the message that we are trying to go across is that if we have any knowledge of the systems, we should include it. And the way to include it is to add either in form of basis functions or of kernel, this information in our prior. So for example, one collaborator of mine showed that the rigid body dynamics of the robots can be written as functions of polynomial basis functions up to a certain transformation of the input. So if we have this knowledge, the prior on our model, so the kernel should be now the sum of, for example, a polynomial kernel that we define here, plus the square exponential kernel. So this will take care of all the modeling effect that we know that are polynomials, and this will take care of everything that is unmodeled and we didn't know how to model. And bringing this a step forward, we can introduce what are called semi-parametric kernels. So in a semi-parametric model, we can conveniently rewrite the initial model as in this form. We still have that the output are equal to f plus some error, but now we split f into components. The first one that is given by the, for example, the rigid body dynamics, so the equation of motions, in which the parameters are pi, and these are the basis function, plus some non-parametric function that is called g. What often people do is that they fix this component, they move it on the left-hand side of these equations, and then they use g in to learn the residual, which is okay. And I think it's a good way to go when we don't have access to the analytical expressions of the basis function phi, which, for example, in if we are using physics engines, we don't have it. But in general, if we have access, we should not do that. What we should do is to put a prior information over pi, over the parameters pi, which makes these basis functions becomes part of the covariance that we know a priori. So we have a kernel that is called physically inspired kernel that depends on the basis functions. And now the same parametric kernel should be the sum of these physics inspired kernel that uses again the basis function of the reachable dynamics plus the any non-parametric kernel, as for example the square exponential. So what the message that I really would like to take to say here is just that if we know anything about the physics, even that if it is exact, or like in the case of the base function, or if it's an approximation, we should include it because it's easy to include it in our priors by writing the corresponding kernels and just simply adding it to the non-parametric kernel that we are using. And this, for example, is just one application of these same parametric kernels that we applied to, again, to these maze systems. Yes, we worked quite a lot on these maze systems. And it's a fairly complicated dynamics, but we were able to learn it from scratch using this same parametric kernel and Gaussian process regression. We can now present the second contribution of the in the model learning block of our algorithm. And usually what we see in literature is that we predict one component of the state. I mean, each and all components of the state with one independent Gaussian processes. So what we assume is that basically all the state components are independent, and we learn as many Gaussian processes as the state dimensions. What we are proposing instead is sorry, there is some noise outside, is speed integration. What we mean by that, usually we can represent a mechanical system's state as composed by position and velocity. But what we know is that under the assumption of constant accelerations between two time steps, we know the relationship between the evolution of the velocity and the evolution of the position. So what we are suggesting is that a more principled way to learn the model of the dynamics is to learn a Gaussian process only to start to learn the evolution of velocity. So we'll have to learn half of the models, saving computational power. And we are not solving a static map anymore, but now we are actually exploiting the relationship that the gives tell us between position and velocity in this case into our Gaussian processes. And this would kind of open a bit more broader questions on in which space we should really do learn our data-driven models, and maybe we can discuss about it later. But the point is that all these properties, including physics, I mean, all these ideas of including physics into our model with the prior or with this speed integration approach have very strong effects when we are modeling long-term evolution of the systems. If you're just looking at one step ahead, often even deterministic models can have decent performances. But for this kind of algorithms, we really need to be able to describe correctly the systems for many steps ahead of us. So including the physics has strong benefits in these regards. Okay, next we are going to talk about the policy learning aspect of our algorithm. And the general objective in policy learning is to find a function that, given the state, outputs the control input that minimizes the expected long-term cost. That is the sum in all the time instance of our our rollouts of the expectation cost of the cost function. Expectation with respect to the distributions of the states. So indeed, in order to compute this, we need to know the state evolution px of 1, px of t. So for all the state, what is the distribution of the states? And in general, this implies that we have to apply in cascade all the GP models one after the other. So at a general time instant t, the distribution of the next time steps x of t plus 1 would be given by this integral that unfortunately is generally untractable. And this is a very well-known problem. How people try to solve this? Well, for example, in PILCO, that it's an algorithm similar to our, where they're also using Gaussian process regressions, but they learn the state evolution by point matching, which I think can be well understood by looking at these pictures, because at certain time instant, they assume that the distribution, the joint distribution between the states and the input is Gaussian. They feed this into the model, the F that is learned so far, and the output, so the evolution of the state, would be the green curve over here. What we are saying is that they can fit a Gaussians into distributions, and they have a principal way of doing it. And the nice thing is that then now they can know in closed form the how to propagate the uncertainty from one time step to the other, and they have an analytical form to compute the gradient, the policy gradient, and so they can propagate it through all the time steps. The disadvantages are, though, that they could do it only with some specific kernels, and of course that they can have only unimodal distributions because they are forcing the distributions, the posterior distribution, to be Gaussian. What we are proposing instead is, and we and other people before us did, is that we can sample from the initial distribution and particles, in this case 2. For each of them, we apply our Gaussian process model that gives us a posterior distribution that is Gaussian. From the posterior distribution, now we sample only one or more particles again, and now we know that the posterior distribution of this particle will be again a Gaussian. So we can keep iterating like this one, and we can have an estimate of the distributions, where now the uncertainty of the systems is separated but learned by propagating all these particles. The advantages of this scheme is that, well, we are not imposing any structural approximation on the distribution of the states. And also the initial condition can be arbitrary, doesn't have to be Gaussians as it was before. And the good thing of this one is that now we don't have constraints on the choice of the kernel function. But as we saw before, introducing all the concept of introducing physicity into our priors, into the kernels, we need to have freedom of doing that. So this enables us of choosing any kernel. Of course, there are some disadvantages in computational complexity, but since the evolution of all the particles is independent one another, basically we can exploit parallel computing in order to compute them. So many people have worked on it in the past, trying to this kind of extension to Monte Carlo with particle-based ways of evolving the state evolution, but they had problems in local optima and in gradients estimation, because there are the famous phenomena of exploding or vanishing gradients. So now, during policy optimization, we see what is our approach to try to solve these kind of problems. First of all, let's introduce the policy structure that we're considering. It's a radial basis function network that is basically just a weighted sum of exponentials. This is our policy, but could be any differential functions, like a deep neural network. And the way we compute the gradient is that we approximate the expectations at each time steps by using the particle. So now it's an average of the cost at each time step through all the functions, and then in order to estimate the expected cumulative cost, we just sum all this expectation through all the time steps. But if the sampling, in order to estimate the gradients, we need to propagate backpropagate the gradients through all the particles and all the time steps. For doing so, we are using the reparameterization trick. Because if we would sample directly from the posterior distribution for each particles that we know is Gaussian, we would not know how to do it. So the reparameterization trick simply says that, well, we can sample from a Gaussian that has zero mean and the covariance matrix is the identity, and we can scale it through the Cholesky factorization of the covariance functions of our Gaussian process, and adding the mean of our Gaussian process. So we are sampling actually from the same distribution, but now since we know the dependency of these two components with respect to the theta, the parameters of the policy, well, we can easily compute the derivatives of these guys. And so we can compute we can propagate the gradient through all the time steps, and we can have an estimate of the gradient of the cost functions. And with it, we can update our policy. The problem, though, is that this effect of vanishing and exploding gradients and local optima is still there. And so what we actually, our contribution is in trying to, we propose to add the dropout, which is a famous technique in using deep learning. But it was used for supervised learning, in classification problems and so on. But what we are doing here is we are applying it to control problems. So we are using Turing policy optimization, and at each evaluation of the policy function, the policy weights are randomly dropped with a certain probability, which really means that we are obtaining a parameterized stochastic policy. And the advantage of this is that we are increasing the entropy of the particle distributions, because we have basically simulating many different policy each time, and which results in better properties like escaping from the local minima and this mitigating the exploding gradients. We verify this empirically. But the idea is really that since we are at each time steps, at every time step we have different policies, we are really kind of having a regularization effects on the gradient estimates. Though the disadvantage is that if the policy is stochastic, in the end, we don't want a stochastic policy, because when we will implement it on the robot, we want to have a deterministic policy. So in order to improve the final performances, we added an heuristic to decrease the dropout rate gradually. Actually, the heuristic was not so simple, but we don't have time to enter in the details. But basically, with a certain rules, the dropout rate, so the probability goes to 0. And so in the end, we start from a stochastic policy to solve all the optimization problems. But finally, we arrive to a deterministic policy that is the one that we will deploy in the algorithm. With this, I have concluded the explanation of the overall algorithm. And just to summarize, our contribution with respect to the structure of the model-based RL algorithms. So we have introduced structured kernel based on physics and the speed integration schemes. And we could do this really because we are using particle-based methods, and we were actually able to successfully use these particle-based methods by introducing this concept of dropout. And actually also by doing some analysis on the cost functions, that is actually very important, I think, for these kind of problems, but we don't have time to really get into the details. Very quickly, we can go through some state of the art. PILCO, we just kind of mentioned before. Another important one is black drops, where they also use the Monte Carlo method for propagation density, but they were using a black box optimizations, so they were not estimating any gradient. And they obtain similar data efficiency with respect to PILCO, but slightly better asymptotic performances. Then I would like to point out that in a PhD thesis in 2014, they tried to apply PILCO to Monte Carlo methods to PILCO, but they failed for the problems of local optima and gradient estimate. Recently, they have proposed this algorithm called PIPS, in which
I didn't get that. Could you try again?
Sorry, in which they tried actually Monte Carlo. Sorry, Siri is not letting me alone. In which they tried to apply Monte Carlo methods with the reparameterization trick. It's exactly what we did. And what they found out is, again, they even said that it's not only a numerical problem what you obtain, but it's actually a structural fundamental problems. So their solution was to try to to add on top of the reparameterization trick another criterion that is called likelihood ratio. And in the end, so they were able to solve more problems than PILCO, but obtaining similar performance to PILCO in systems that they could compare to. And finally, there are some PILCO-like algorithms that uses neural networks that we are not really considering because of problem of data efficiency. Usually when we are using these large deep neural networks, they are much more data eager. So we can finally get to some experiments. And let me first just introduce the carpole that is used as a toy example, just standard carpole, and we want to swing it up. And all the experiments that we are going to see here, they will be a Monte Carlo study composed of 50 experiments in which we are we have different random seeds, so different initial conditions and different noises. And each experiment is composed of 5 trials of 3 seconds each. First of all, I would like to show you one ablation study. So if we are considering or not the dropout. So in this figure, we have on the bottom, what we see is that all the trials, the 5 trials that we have trained our algorithm into, and of the y-axis is J, the long-term cost function. And the full lines are the medians of the performances on these 50 experiments that we have seen, and the shaded area is the area between the 5th and 95th percentile. What I would like to is important to notice here is that, well, not only we are doing slightly better in median, but not very much, but the use of dropout makes so that the uncertainty, I mean, the variance of the performances is decreasing, and in the end, there is no more variance in the performances, which means that we're able to solve for all the 50 different random seeds, while without using dropout, there is still a lot of variability. And in this table here, we can see indeed the successful rate, and indeed, not only we do much better at each trial compared to the previous one, but also at convergency, the use of dropout makes us converge and be able to solve all the 100% of the experiments. We then compare MC-PILCO with some meaningful state-of-the-art that are PILCO and black drops. And again, here we have the same graph, and here we can say again how we have better performances in median, but especially into the variability. So we are able, again, we are the only algorithm that was able to solve for all the 50 random seeds, and while the other 2 algorithms had problems. And notice that in here, we were just using, for example, the square exponential kernel as a prior information, just to be fair with the other algorithms, and we didn't use more structured kernels. Finally, I was talking about multimodal distributions and our ability of our algorithm to handle multimodal distributions. So again, we try to vary the initial condition of the card, moving it, starting from the left and the right. So you can imagine that the pendulum should be swinging to the left or to the right or to the left directions accordingly. And our algorithm was able to clearly find 2 different modes of policies. And you can see it here, this is the force, so it's the input, and we have 2 different ones, and so according to the initial conditions, we have 2 different movements of the pendulum, of the pole, while PILCO not only most of the time was getting confused and was not able to converge, but also always can find only one kind of policy, which of course it's suboptimal and and so it doesn't really find the optimal final policy. And this is the last simulation experiment that I want to show. That is we want to show that this algorithm can be extended to a bit more complicated systems with a higher dimensional state space. So in this UR5, for how we represented the state dimension was 18. And we applied our algorithm to do trajectory tracking for the end effector of the UR5. And here we can see all the training. So we started with a purely tuned KT, collected 4-second experience. Then we did 1 trial of our algorithm, and we can see how it was improving the performances. And then in the end, after 8 seconds of experience, so we collected only 8 seconds of data, the algorithm was able to learn the policy to do the trajectory tracking. All these results are properties. I think they are very interesting, and we kind of gave an idea of the different aspects that we are able to solve. But what we really want is to have this algorithm working in real systems. And so we are entering the final part of the talk. And the problem for this, when we go to real systems, is that in mechanical physical systems, we cannot measure the full state, but maybe we can learn just measure only a subset of it. For example, in mechanical systems, usually we can learn the position, but not velocities and accelerations. These are, for example, just 2 systems that we are where we found this problem. But in general, when we do robotic manipulation, there is already a problem of how to do pose estimation. Definitely, we cannot have access directly to the velocities. And for who has worked in these kind of systems, I think probably found himself in some similar situations where here we just estimated the velocity from the history of noisy position measurements. with different filters. On top of here, we have some numerical differentiation plus low-pass filters, and down here we have some Kalman filters, and then we use the Savinsky-Golay acausal filter kind of to trying to give a ground truth. But basically, in the end, we are always struggling and finding a trade-off between smoothness of our estimates of the velocity and the delay that we are adding to the systems, and we are a bit stuck into this concept. So what is our approach? Well, so what we are doing is we are extending MC-PILCO to partially measurable systems. Sorry. Which are observable systems, but on which only a subset of the state components can be measured. So for mechanical systems, these are only positions, but we cannot measure the velocities. And the standard approach, as we were saying, is to just compute some state estimator on the history of the position. What we are proposing here instead is a small variation, but I will try to convince you that it's principled, and it is to add two state observer, two state estimators. The first one is called offline estimator and is used in model learning. And the second one is called online estimators and is used in policy learning. I think they are principled because models and policy have different purposes. So the model should really simulate the real system dynamics. So we wanted to learn the dynamics of the real systems independently of the noise that we have from the sensing instrumentations. While the policy instead needs to be trained on seeing states that are similar to what it will see at test time. Otherwise, it would get confused when it goes into the real system. And I'll try to explain this in a bit more details here. And so if we look here in the evolution of the real systems, so here we have the robotic systems, we apply certain actions, and this has its own real state that we don't know. Then there's a sensor that gives us the measurement of noisy position. And then we have some online state estimator that gives us the full state estimates by computing numerical approximations, so both for position and velocity, and the policy takes this state approximation and computes the next action in order to control our system. But when you are offline, we have access to the control, to the measurements, and to the state estimates. And what the model learning should do really is to try to learn the relationship that there is between U and Q dot, right? Not between U and Z, what the policy is saying. For this reason, we are proposing, we are saying, okay, at this point, we can use even acausal filters like this ground truth filter that we were talking about before, like Kalman, like the Savinsky-Golay or the Kalman smoothers. And the reason why we can do that is because even if the model learning now learns the true relationship between input and the real states, that is not good when we go into the policy optimizations, when we are doing policy learning, and so during the optimization of the policy, when we generate the evolution of the states using our model, so we obtain something that's Q hat, so something similar, if we learn well our model to the real state, we want now to corrupt it with filters that actually emulate what the policy will see at real time, that is the model of the sensors, and some model of the online estimators. Notice that often this online state estimator, we don't have access to it because maybe it's embedded into the systems, or if we do, we can just replace it. But the advantage of this one is that the model learning can really learn the dynamics of the real system that helps in this long-term state descriptions, and the online estimators instead just change the model predictions in order that the policy is trained on data that resemble what we'll see at real time. We had a proof of concept here on the carpooling simulations, but maybe we are a bit short on time. So let me just skip to the experiments on the real systems. And these are the two real systems that we are going to consider, the Furuta and the ball and plate. And for the Furuta pendulum, that is kind of a more complicated inverted pendulum because the arm moves in a rotatory axis, and the goal is still to swing it up. And we use as offline estimator central difference and as online estimator the final difference. For the ball and plate instead, where the purpose is to stabilize the ball in the center, there is a camera on top here that gives us both estimations, so of the position of the ball, but this is much more noisy, and we use as an offline estimator the Kalman smoother and as online estimator the Kalman filter. Now let's see how it works in when we try to solve it. And what we're going to see here is the whole training on the real systems and the final policy. And also I will show you 3 plots that compares the performances of 3 different kernels, as we were talking before. So we are going to see the square exponential kernel, the square exponential plus polynomials, and the same parametric kernel on the right. So we start with a random exploration. Then we compute the first trial, and this is how our algorithm is learning according to the different kernels. And we can see that the same parametric kernel that is here on the right, after only 9 seconds of experience, is able to learn the final policy. The polynomial kernel is able to learn it after 12 seconds, and the square exponential will be able to solve it after 18 seconds. So here is, again, all this concept of data efficiency that we were talking before. Now we have been able to learn these fairly complicated systems in 9 seconds from scratch, which means using 270 data. So not thousands, not hundreds of thousands, not millions of data, but 270 data. And we have seen how the structured kernel learn in less trials. And here we are seeing how the learn policy is robust to unknown disturbances. Finally, this is the last video, and we are going to see the same for the ball and beam systems. Here again, we are seeing all the data that the algorithm has seen for training. So we have 5 seconds of explorations. Then we go with our first trial of our algorithm, MC-PILCO for PMS algorithm, then a second trial, and now after 11 seconds, we were able to learn the policy. Again, which means that in 340 data, we were able to solve the task to stabilize the balls, starting from each and all the initial conditions on the plate. I'll just skip ahead a bit for the sake of time. And we are also robust to some disturbances if we are trying to move the ball around. With this, I've concluded. Just quickly some main messages. I hope I convinced you why it's important using probabilistic models for this kind of systems, because really they reduce the bias by handling the uncertainty. And we kind of propose a solution to the problem of doing gradient estimation using Monte Carlo methods by using by inserting the dropout and adding this dropout rate reduction. And if you're interested, we are going soon to be released the code, the full code of MC-PILCO in our website. And with this, I can conclude. We don't have to enter the details, maybe because we are a bit out of time, but we have presented the main ingredient for model-based reinforcement learning. We presented MC-PILCO that can handle multimodal distribution, is data efficient, and can handle uncertainty. And we saw how to how it works when it goes into real systems. And in the future works, we are actually really want to extend this to manipulations and assembly problems. And we want to keep including physics engines, add safe explorations, and really think on how to deal with long-term planning horizon problems. I just would like to thank and acknowledge the contribution of all my co-authors. These are my co-authors for MC-PILCO. In particular, Alberto and Fabio have done a lot of work into it. And these are other collaborators that with which I made the papers that I showed you in the beginning of the presentation. Thank you all.
Thank you, Diego, for the great talk.
Thanks.
Are there any questions from the audience?
Either I've been very clear or not at all.
Question, right? So I understand why, when you do the model learning, right? So you don't restrict yourself to online, right? But in a sense, learning the model doesn't defeat a little bit the purpose of the policy learning?
I mean, it's of course an interesting question that probably has many answers, but I would say no, because the models can be learn independently of the task and can be used to learn many other policies. So usually the policies task dependent or constraint of family. Instead, if we learn the model, then we can use it to learn several tasks much more efficiently.
Right, but then if you have the model, then you see the two as a little bit independent in a sense, right? Or like different approaches. So yeah, you can use both, right? But
sure. I mean, they are independent in a sense, and the model could be used in totally different other schemes. I mean, this same model could be used for an MPC controller or any kind of controller, and so the policy learning that we did is a choice.
All right, but once you have the model, then what's the point of reinforcement learning in a sense? So
that's true, but
and I understand that if you use both, I mean, the more the merrier, right? So it's just that.
No, I understand the point. So if we would know the exact models since the beginning, the whole concept of these trials would not be needed. But in practice, we need to keep collecting data to really have a model that is good enough to solve our tasks. And so here is the concept of several trials, and at each trials we can improve the model and the policy, and we keep it.
Okay, so in a sense, is the fact that the fact that the model learning is offline doesn't necessarily mean that it's done, right?
Exactly.
It's kind of offline. So and you keep learning on both sides in a sense.
That's exactly true. Yeah, that's correct.
Got it. Thanks.
Thanks.
Any other question?
Maybe one from my side.
Go ahead.
Can you say anything about constraint satisfaction of your policy?
Sure. So in this, we actually had some constraint satisfaction in this case, that because that we added only in the cost functions in this case. So for example, when we are dealing with the Fruta pendulum, the cost function, we didn't want that the arm of the Fruta was going too much, moving too many degrees, too much on the left or too much on the right. And so we had to add this constraint in order to avoid that the pendulum was doing the full loop. So it is possible to add them. And in general, what we are solving is really an optimization problem. So we, in this case, we were using the Adam optimizer, but we could add any constraints that that we would like to solve into the optimization problems. In this case, we just added as part of the cost functions, but we could write them down into the optimization algorithm itself. And again, since the model and the policy are kind of independent, there's no harm in doing that.
Thank you.
Any closing question? If not, I think we can thank the speaker. Thank you very much, Diego. I think you left your contact if somebody wants to reach out.
Absolutely. Yeah. If anybody is interested more, please contact me, and I will be happy to answer more questions or go deeper in any topic.
Thank you very much.
Thank you.
Thank you very much for the talk, and good luck for your research. Thank you everybody for participating, and see you all next week. Bye.
Thanks a lot.
Thank you, Diego. Bye, everybody.
Thank you for the questions. Bye.